Hi class, this is Sir Alex Basco and welcome to our lesson 3 in General Physics 2. Today we are discussing Coulomb's Law and we'll be dealing with part 1, which is basically I'm just going to explain what Coulomb's Law is, where do we use it, and how it originated, as well as how Coulomb's Law is actually also related to another law made by Newton called the Universal Gravitational Law. So at the end of the lesson 3, what I want everyone to be able to do is for you to be able to use Coulomb's law and sometimes even the gravitational law to calculate the net forces on a point charge exerted by a system of point charges. When we mean point charge, it's basically, you can think of it as a point with a charge. So this charge could be positive, could be negative. You can also imagine a point charge as like an atom or an electron or a proton, wherein they have charges. So later on, we'll explain more about that, as well as for you guys to be able to calculate the electric field due to a system of point charges using Coulomb's law and the superposition principle. So let's begin by understanding what is Coulomb's law. One of the fundamental things that we have learned is that same charges repel and unlike charges attract. We know that if you have two charges, you can think of it as you have two point charges. So I mean you have like a point. So you can think of that point as this red dot right here. And this red dot has a charge. It could be positive or it could be negative. And if there's another charge maybe let's say at this point, and it has another charge, positive or negative. If those charges are same sign, if they're both positive or they're both negative, we know that these charges should repel. But if they are unlike charges, meaning one is positive, the other is negative, we know that these charges should attract. We know that. That's a fundamental knowledge that we should already know by now. But the question that I want you guys to think about is if these charges repel and attract, meaning there is something, a force that pushes them away from each other, which is repel, and pulls them towards each other, meaning they attract each other. So this repel and this attraction, or this repulsive and this attraction, is actually a type of force. I want you to think of it that way. This repel movement and this attraction movement is actually a type of force that pushes the charges away from each other or pulls the charges towards each other. The question is, how do we measure this magnitude of force? Since we've already established that this repel and this attraction is a type of force, therefore we can actually measure the magnitude, meaning the strength, gaano kalakas or how strong this force is. And we can measure that using Coulomb's law. It's Charles Augustin de Coulomb who actually discovered or formulated the relationship or created the formula in order for us to find these attractive or repulsive force. He did it in a way using what we call a torsion balance. So torsion balance is basically designed similar to this, and inside this cartridge right here there is a rod, and inside there is a wire hanging, and hanging on that wire is a rod. So this is straight line right here, you can think of it as a rod. And at the end of each, or at each end of the rod, there are two similar spheres. So they're two identical spheres, okay? And what Charles Augustine did is they used this torsion balance by inserting another sphere onto this hole right here. And what happens is because these spheres right here, the one inserted and the one hanging, has different charges, or they could also have similar charge, there would be torsion. Torsion means it's a type of spin, okay? So if, for example, in this case, this is a positive sphere and this right here is a negative sphere, we know that this sphere should attract. So what happens is that these forces right here would actually start to spin. So this rod right here would start to spin in a way that would attract this sphere right here towards the positively charged sphere. And Charles Augustin de Coulomb calculated the times how much it spent, and by measuring that, he were able to formulate the Coulomb's law, wherein, like I mentioned, we can actually use to measure how much force is being attracted or being repulsed by this force. So he found out that the formula has a relationship between the electric force, the one that we are measuring, the distance between the particles, so in this case, how far this positive charge and this negative charge right here, how far they are. And there's also a relationship between the charges of these metal spheres. So with that, he were able to formulate what we call the Coulomb's law, which states that the magnitude of the electric force, meaning the strength of the electric force between two charged objects, is one directly proportional to the product of the magnitude of the charges, meaning the charge for this positive and the charge for this negative should is proportional in their product. So if you multiply these two values, is proportional to the electric force, meaning if these charges increases, the electric force decreases. Moreover, Coulomb's law states that the magnitude of the electric force is inversely proportional to the square of the distance between them. So meaning the distance right here, the distance between the positive and the negative, the more that you increase that distance, the lesser. No? So that's why we call it inverse. As the distance increases, the electric force decreases. As the distance decreases, the electric force increases. That's what we call by inverse proportion. And the mathematical equation for Coulomb's law is here. So F is basically the magnitude, the one that we are measuring. Sometimes you can also, F basically denotes the force, okay, the electric force. The type of force is an electric force. And since it is a force, we measure it in newtons. So the unit that we use in Coulomb's law is newtons. Q and Q is Q1 and Q2 are basically the magnitude of the charges in coulombs. So the unit that we use to denote how much charge a particle or an object or sphere has is coulombs. We use C. Okay, so as you can see here, use Q, and there is an absolute value sign. So what we have to remember, when I want you guys to remember right now, is when you are measuring the electric force, or how much, or the magnitude of how much attraction or repulsion these two charges are having, you need to remove the sign. So if Q1 is positive and Q2 is negative, just remove the sign, just multiply the two. You can imagine it is basically applying the two numbers without regard for the positive or the negative. So meaning if Q1, Q is basically denoting the particle, okay, or the object or the sphere that has a charge. So if this Q1 is negative and the Q2 is negative, just multiply them without the sign. So that's what you want to do. You want to have the absolute value. And these basically the distance between the charges in meters. So we mentioned earlier that according to Coulomb's law, that the force is inversely proportional to the square of the distance of the two objects. So that's why we have over d squared. Basically 1 over d squared is inversely proportional to f, meaning the more that you increases the distance, the lesser the f is. The more that you decrease the distance, the higher the f is. That's what we call the inverse proportion. And k is something that I want you guys to memorize now. K is what we call a proportionality constant. So it's a constant number. It doesn't change. In this case, what we call a Coulomb's constant. And the value of Coulomb constants is 9 times 10 raised to the ninth, Newton meter squared divided by c squared. So I just want you guys to remember this for k, because k again is a constant. It doesn't change. This is always the value of k. The only thing that it changes if you're measuring the two objects when they are not in the air or in a vacuum. So imagine if these two q's are in water, this k would change. But for most of the time, we are measuring the two objects or the two charged particles or two charged objects in either air or vacuum. So just use the value for k. And lastly, that I want you guys to remember, F is always positive, okay? But this is one thing that I want you guys to remember. It's a vector quantity. Remember what vector quantity is? Vector quantities are quantities that are measured by their magnitude and their direction, okay? So that's the difference between scalars. Scalar is basically just the magnitude. Example, your age, it's just a number. But for vector quantity, we also measure the distance, or not the distance, the direction. That's what vector quantities are. It has a magnitude and a direction. The magnitude of the force is always positive. But if you see a sign in front of it, so basically you can sometimes see negative or positive, that is just denoting the direction. That is not the value of the magnitude. That's just the direction. I want you guys to remember that for vector quantity. The F is always positive. The value is always positive. The magnitude is always positive. But the direction can be negative or positive. So the negative and the positive sign that you put on your F is basically the direction. This is important to remember because when we start talking about superposition principle, I don't want you guys to get confused. So just remember that. And the direction is always along the line of the charges. So if you have two charges here and you have another charge over here and you connect them by a line, so the direction of the force is always along that line. Okay, so I want you guys to remember that. So that is what Coulomb's law is. So at this point, what I usually do is give you some examples, sample problems, but we're not going to do that yet. We're going to do that in part two. So for the next uploaded lesson, that's where we are going to do all the computations and the sample problems. So for now, I want you guys to remember the theory behind Coulomb's law. And especially this part right here, the relationship or the difference and the similarities between the Coulomb's law and Newton's law on universal gravitation. So you can think of this, Coulomb's law is when we are pertaining about something that can be very, very small, even electrons and protons. Electrons are negative, protons are positive. We know that from chemistry, we've talked about that. And you can actually measure how much attraction or how much repulsion these electrons and protons can have using the Coulomb's law. While Newton's law on universal gravitation is what we use to measure the force of gravity between two massive objects. So you can think of it as the sun and the earth. The sun and the earth are two massive objects. But because of their mass, because they're so big and they're so heavy, they tend to have a what we call a sort of a pull. And this pull is what we call gravity. When objects are so massive, they tend to have a very high gravitational force. And we can measure how much attraction or force or gravity is being is being caused by these masses using the using Newton's law on universal gravitation. So meaning Coulomb's law, we can actually use it in a very minute objects, very small objects, and Newton's law is what we use with very massive objects. So you can think of it, so they should be different, right? But in reality, if you look at them, they're actually not very different because this is the equation for the universal gravitation law. You have Fg, I just denoted with G because they're both forces. So we can use F. So I just use sub G to denote that this is for gravitational force. Is equals to G, which has a value. This is another constant. The mass of the first object, so you can think of it as the mass of the sun or mass of a planet 1, and then another mass of another planet, and divided by the distance of those two planets. And then look at Coulomb's law now. Coulomb's law, I just put E to denote electric force because we are talking about electric force here. We're talking about gravitational force here. And if you look at them, you can see that they're very similar. So you have a G constant here, and you have a K constant here. G has its own value as well. I can't remember the top of my head. I'm just going to remind you guys later on what G is, but it's also on the module. So just look at the value of G on the module. But as you can see, so the forces for universal gravitational law and the Coulomb's law, these two laws basically share the same form. Both follows the inverse square law for the distance. So each forces follows the inverse square law, meaning as you increase the distance for both, the forces decreases. As you decrease the distance for both law, the force increases. Moreover, they're also following another proportion, which the product of the two quantities causing the force is proportional to the force. So meaning the force, the gravitational force, the cause of this force is actually the mass. So again, if things are very heavy, they tend to have a massive gravity, and that gravity is caused by the mass. Okay, so if you multiply the mass of those two objects, it is proportional to the force of gravity exerted by the mass. So meaning if I increase the mass, the force of gravity also increases. The same is true for Coulomb's law. If I increase the charge of one particle, the force increases. So that's why they are directly proportional to the product of the quantity that causes the force. So for gravitational force, the quantity that causes the force is the mass. For electric force, the quantity that causes the mass is the charge. Okay? So by multiplying those values, you can directly proportionally get the value of the force. But lastly, there's also a little bit of difference between the two. Gravitational force is only attractive, okay? It's never repulsive. So for gravity, it's always the thing that pulls you to it. That's why we are always stay on the earth, because the mass of the earth pulls us towards the earth. Hence, we stay on the earth. We stay on the ground. We do not float into the sky. But for electric force, depending on the sign of the charges, could be positive or negative. It could be both attractive and repulsive, or both attractive or repulsive. Again, when you multiply the two, just remove the sign. But when you're considering whether it is attractive or repulsive, which basically tells you the direction of the force, you have to remember which sign the particle is. So if my Q1 is positive and my Q2 is negative, we know that should be attractive because same or unlike signs attract. If Q1 is positive and Q2 is positive, we know that it should be repulsive force because same signs repulse do not attract, okay, push away from each other. And generally gravitational force is weaker. So those are some of the things that I want you guys to remember about Coulomb's law and Newton's law in gravitational or universal gravitation. So that is the lesson part, lesson 3 of Coulomb's law part 1. We're gonna head next time we're gonna discuss the part 2, which is basically an application of Coulomb's law and the universal gravitational law on sample problems. If you guys have any questions, do not hesitate to message me, and you guys have a great day.